All right, good morning. Today I'll be competing in round 650, Div3. So again, not rated for me, but should be fun. As usual, I'll just be mostly competing during the contest, and then afterwards I'll comment on the solution ideas to all of the problems that I think I have solutions to, or that I have figured out. So if you're interested in the solutions, probably skip to the end. If you want to see me compete and like my train of thought, or you just like to watch me struggle on easy problems, then feel free to watch the whole thing. Yeah, we'll see. Today I have my my bot that I programmed announcing the verdicts, so I shouldn't need to look at Codeforces. I should just be able to hear them. It's got a little victory jingle every time I get a problem right, so hopefully I'll get at least one of the Div3 problems right, and we'll get to hear it. Good luck, have fun. String A has length 2 or more characters. Then he builds a new string B and gives Alice B. So presumably we have to guess A. Okay. So then Bob builds B. He writes all substrings of length 2 in order from left to right and then joins them. So like AB. Yeah, okay, so it's every other letter and then the last 2. How many test cases? It should be fine. ABAC, blah, 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 bunch of Z's, looks good. I don't know, I'm on Java 11, I want to be on a different Java 8, but not an issue for now. All right, you're given an array of length n. There's the jingle. You're given an array of length n, which consists of non-negative integers. Note that the array indices start from 0. An array is called good if the parity of each index matches the parity of the element at that index. So this is 1, 2, 3, 4, so that means it's good. The minimum number of moves to make the given array good. So what are the moves? In one move, you can take any 2 array elements and swap them. Is the first index 0? Yeah, so I guess we have to swap these 2 and these 2. And then we print -1 if it's impossible, is what I'm assuming. Yeah. Okay, so we need to make sure the number of even indices matches the number of even numbers. So in this case, you just swap these 2. Yeah, so if the parity doesn't work out, then we're in trouble. Otherwise, it's just the number that we have to swap. Okay, then for, well, I guess int evens. If I mod to 0, so n divided by 2, but really n plus 1, and then odd spots is just n over 2. Yeah, okay. So if evens not equal to even spots, or odds not equal to odd spots. I guess those are always going to be the same value, but that's irrelevant. Take this out, -1. Else, this out wrong evens. So if we have an even at an odd spot, then wrong evens plus. Oh, this is only if index mod 2 equals 0. Two, 1, -1. This one's 0. Why is that the case? Even, odd, even, odd, even, odd, even. So the number of even spots should be 4. 1, 2, 3, 4. The number of odds should be 3. 1, 2, 3. Oh, this is backwards. Cool, looks good. And then we'll listen for the result.
Well done, sir. I see you on
There we go. So we have a binary string basically. And we need to social distance. And this is a common theme these days. Okay, so yeah, so we gotta keep these far away from each other. Keep the ones far away from each other. Yeah, blah, blah, blah. All right. If the restaurant is described by a string without a 1 or a string with 1, 1, then it's satisfied. Yes. You're given a binary string that describes the current state of the restaurant. Okay, find the maximum number of free tables that you can occupy so as not to violate any rules. What if it's already invalid? Is it guaranteed to be valid? The given string satisfy to the rule of the restaurant. Okay, I think this means that it will be valid. This is oddly written, but that's fine. So test case starts with 2 lines considering, and okay, so all right, so what about 2? Less than or equal to 2. Okay, so this is just greedy then, obviously. I guess we just need from right, because then I'll do a left sweep at the end. So I go from the right to the left, and then if line I equals 1, then right count is equal to 0. Else right count plus plus, and then from right I equals right count. All right, so then if int right, so then we want to say if left count at I is greater than k, and right count at I, or I guess it's just an integer, and this is not that name, from right at I is greater than k. If that's the case, then plus left count is 0. So if line at I is equal to 1, then left count equals 0. We need to continue. Otherwise, left count plus plus. I think that should handle it. It's a lot of logic going on there, but okay, so it doesn't handle it at all. So this should be 1. All right, so let's so this is 0 from the right. Okay, that's fine. This is 3, 2, 1, 0, 3. 3 is a bit interesting, but I guess that's fine. Oh, is this because we're incrementing before we're supposed to? No, that should be fine. Sure. All right. So then here it should be 0, or here it should be, yeah, here it should be 0. Then here it should be 1. And then here it should be 2. So this needs to be this. All right, 1, 2, 0, 1, 1, 1. Nice. Do we need print writer? I guess it doesn't hurt. All right, so that should be fine. I guess let's just run it once more to sanity check. Cool. Submit C. Nope, C please. Did I see or one of these problems? We've got easy and hard. That's fun.
Well done, sir.
There we go, we got it. I guess, well, this shouldn't be that hard. Task and a board. All right, you've got a board. Well, fine, let's look at the standings, see if this is someone trying seriously or not. Doesn't look like it. 300 IQ, yeet. What a man. All right, so let's read D first. String is known for you and given in the input. Yes, all right, so we've got some string. You're given a sequence of m integers where this is the sum of distances. What? I'm very confused. Suppose that string t has length m and the characters are numbered from 1 to m. All right, that makes sense. You're given a sequence of m integers where this is the sum of distances from index I to all indices j after it. In other words, to calculate BI, Polycarp finds all indices j such that index j contains a letter that's later in the alphabet than I and sums the absolute value of the distances. Okay, I think I see. So if it's A, B, A, C, then it's 1 plus 2 plus 3. Got it. So for if it's B, you only look at stuff that's strictly after you, so it would be 1. All right, so then this is 0. This is also 1 for the same reason. Given a string S in the array B, find any possible T. What is T? Oh, I see. It's guaranteed. Man, stop saying this, please. No one knows what this means. It's not clear if it's like always true or if it's like, what does this mean? This is a very unclear sentence. Statements should not have this sentence. It's guaranteed that any, like, what does it mean that it's guaranteed? Does it mean by the properties of this problem, it will always be the case that this is true? Or does it mean the only input that's valid is input for which this is true? Like, this is super ambiguous. This is a very, like, stop saying this, please. All right, anyway. Number of test cases in input. Then Q test cases follow. Each test case contains 3 lines. The first is string S. All right, so let's look at this, I guess. So T has length 3. And the numbers are going to be 2, 1, 0. If we look at the numbers in increasing order, does that necessarily go from smallest to biggest number? Oh, I guess bounds are really small, so probably do something creative here. It seems to me like it isn't necessarily true that if you, like this biggest number here, so the biggest number here is a 2. In this case, it probably corresponds to an A. But it seems like that's not always the case. So here, the answer is AAB, right? I guess AAC works too. But it seems like you could come up with input in which that wouldn't be the case. Like, there are definitely strings where if you've got like a B really far to the left and then an A in the middle and everything else is Z's, then the B, it feels like would have, even though the B has the A to the B distance added in addition, or sorry, the A has that distance added in addition. The B has a much larger set of distances. Well, this is a not super obvious problem, in my opinion. Look at this one. A store sells n beads. The color of each bead is described by a lowercase letter of the English alphabet, A through Z. You want to buy some beads and assemble them, or assemble a necklace from them. Fantastic. Set of beads in a circle. Store sells ABC, ACC. I feel this is some deja vu. I feel like I just talked about this. The following necklaces cannot be assembled. Yeah, so like you can take any of these and put them in any order. I see. This has too many A's. This has a wrong letter. Okay, so it's beautiful if it has a like period of K, pretty much. This necklace is 3 beautiful, 6 beautiful, 9 beautiful. Yes, I see. Alright, you're given N and K, and also the string S, blah, blah, blah. You can buy any subset of beads and connect them in any order. Find the maximum length of a K beautiful necklace you can assemble. So this is the store, right? So that order doesn't matter at all. But here you could do ABC, ABC. So the answer is just going to be a multiple of K. Surely? Oh, well, it might be divisor of K too, I guess. Oh, that's not even true. Yeah, it might be neither a multiple or a divisor. It can just be some other random number. Well, it's only the random number if you only have like one letter, I think. Like if you have just a single letter, it can be, you just take all of that letter. If it's, it might be any divisor. Alright, so what can we do? Well, we can do like all one letter. That's quite easy. What else can we do? We can do I suppose we can't do a multiple, really. Yeah, only factors are relevant. Because if its period is like 24 and K is 12, then it's not 12 beautiful, it's 24 beautiful. So then I suppose 1 is a factor, so this is kind of redundant. So then the period is some factor of K. So maybe we can brute force what this factor is. And if we brute force the factor, we can binary search how many times we're going to make it. Yeah, I suppose that works. So then the runtime will be, we'll binary search how many times we can make it. What's that? That's log n times the number of factors, which is, I don't know, cube root of k to the 1/3. And then each of these takes order, is it only order 26? So I guess maybe we don't even need to binary search. We can just iterate through them. Okay. Yeah, that's definitely easier than D. Oh wait, you can. Order doesn't matter, right? There's no reason. Yeah. Yeah, you can connect them in any order. Cool. So now we have the counts of each letter. For int period, where period is 1, period less than or equal to k, period plus plus. If k mod period is not equal to 0, then this is not valid. Cool, so now we can store our answer. And then we need to keep track of the number of times, right? So int times equals 0. N time, well, surely at least 1, otherwise it's not helpful. N time, that's just true. N times plus plus. And then we want to, so int for length, yeah, length equals 0. So for int I in counts, do we have to print what it is? No, nice. All right, so then int spaces will be equal to the, well, I, the number of these things divided by n times floored. Length plus equals spaces. And then I guess let's make this a long because I don't want to think about it. So then if length is less than period, then break, because doing any more times won't be possible. Otherwise best equals math.max best n times the period. And that should cover all possible things that we might be concerned with. 6, 3, 5, 4, 15, 10. Let's double check. Do we need print writer? Nope, we're fine, I think. Okay, so D seems tricky. I don't know how to do D.
Well done, sir. I see you on call for duty.
Maybe I'm just not seeing something obvious. I might just come back to this. Let's just check my friend's sanity check here. Yeah, so geothermal can get it. Other than that, not much. So let's, oh man, geothermal's not even getting F though. I guess we'll read it. This is an easy version of the problem. In this version, all numbers in the given array are distinct and the constraints on n are less than in the hard version. The numbers are distinct, okay. Given an array of integers n, there are no equal elements in this array, but that isn't true for the hard version, right? Yes, okay. You can perform the following operations. Choose any index and move the element at AI to the beginning or move it to the end. For example, if n equals 5 and n equals this thing, then the following sequences of operations can be performed. Do we have to like sort it or something? Yeah, we have to sort it. This is a good problem. This seems like an actually interesting problem. Minimum number of operations to sort the array, where you can move something to the beginning or to the end. It's very intuitive. After performing the operation of the first type to the second element, the 7 moves to the beginning. Okay. After performing the operation of the second type to the second element, after this, then the 4 goes to the end. You can perform any number of operations of any type in any order. I see. So it seems like a good approach might be keep track of how to do it. Like if you can only move things to the beginning, the answer is rather easy to calculate. You leave some increasing sequence ending at the biggest number, and then for everything else, you just have to move it to the beginning. So now what's the difference here? Well, in this case, there's some increasing sequence that we can keep and everything. Do we have to output how to do it? No, just how many. Is it really just the longest increasing sequence? Because you get to keep anything that you want, and everything else has to be moved either to the beginning or to the end. Like if you look at which elements aren't moved, you don't get to keep anything. You get to keep any continuous range of elements. So here you could keep 3, 5, 7. Move the 8 and the 1. So the answer here is 2. Yeah, this is a fun problem. I like this problem. I don't really enjoy problem D, despite problem D being easy. I also, I don't know, maybe I'm not seeing something obvious. I'll come back to problem D. I want to solve this one first. I want to spend an hour on this at least, because this is a cool problem. So what's our time limit looking like? Pretty average, unfortunately. Well, we can simplify it if instead of looking at the smallest and the biggest number, we look at the second smallest and second biggest number. So we can, like, what can we do? We can take all of one number, because that's always going to be fine. Then I guess we can take all of two adjacent numbers as well. We might as well just coordinate compress, so there's no reason not to coordinate compress. Or we can't take all of two adjacent numbers, but we can take like some prefix of two adjacent numbers. Yeah, I guess we can just try every pair naively. Like, just build the array of just those two numbers and then try that. Because then every element will only be added to two different lists. All right, so now in all other cases, what we're going to do is we have the first index, like the first I, and then the last J. The last thing, well, first thing greater than or equal to I. No, not greater than or equal to, what? I guess the first I. Man, this is kind of an annoying query. And then the last thing greater than or equal to I and less than or equal to J. So we need the first of one thing, the last of some other thing. And then in addition to that, we want to do these range queries. How many of this thing are in this range? Well, how many of this are in this range we can do with just a binary search, or probably with a tree set even. But yeah, I think a binary search will be easy. So we can do a binary search for that. And that will answer that query. So after that, we're left with the problem of given, yeah, we can try every pair of two adjacent numbers pretty easily. So if we know the first element, oh, that's not really the question at all. The question is, how many can we, yeah, this is not the right query. That's an unhelpful query. The query is like, how many numbers, like what's the biggest range that works with this number? Or I guess how many numbers work starting at this number? Is that the same question? It's a very similar question. So how many numbers work starting at the first x? So, well, we need to keep all of the we need to keep all of the x's. That's not really an argument. And after we keep all of the x's, we want to know where's the first x plus 1. Yeah, okay. So I think we can solve the problem then. Cool. What problem is this? This is problem F. Alright, so then hash map, or I guess it's hash map. And then int index 0 for vowels dot put I index plus plus. So now we have coordinate compressed. So now array list integer array pairs. Well, what do we want to do? We need the first and last of each thing. So arrays.fill first index of with n plus 1. Arrays.fill last index of with negative 1. Equals 0. First index of at I equals math.min. First index of a at I and I. And last index of is going to be quite similar. The last index of this thing, or this index, alright, cool. So now we have the first and last index of each number. So int array number occurrences occurrences at a at I plus. Okay, so now we know how many times each thing appears, what the last index is, and the number of occurrences. So one candidate answer. So yes, this is our answer, equals 0, and I occurrences. Then ants equals max.max of ants by this out, n minus ants. That will be our final answer. Okay. So now we can also do any pair of numbers. Do we need any pair of numbers? No, we don't need any pair of numbers. We don't. Okay, so array list integer. Occurrences at I equals new array list. Okay, so then occurrences at a at I dot add I. So n in range. List and L and R. Okay, so this will tell us how many things are in this LR range, assuming list is sorted. So, int mid or min equals, well, we want to find the first index greater than or equal to L. So int min equals 0, max equals n plus 1. And equals this dot length or size. Well, I guess let's handle the 0 cases first. So if list dot is empty or list dot get 0, the first thing is greater than the biggest in our range, or list dot get size minus 1. Come on. If this thing is less than L, then return 0. First index greater than or equal to L. So, well, min is not equal to max, then int mid equals min plus max. So 2 if list dot get mid greater than or equal to L, then min equals mid. Otherwise, wait, if it's big enough, yeah, otherwise it's too small. Well, if it's too small, then min equals mid plus 1. So then if it's big enough, that means max equals mid. All right, cool. So that is fine. So int first legal equals mid. Or equals min. Okay. So min equals 0. Max equals n minus 1. Last index less than or equal to r. So while min is not equal to max, int mid equals min plus max equals 2. List.get this thing, it's less than or equal to r, then we're safe. Otherwise, well, if it's too big, that means max equals mid minus 1. If it's small enough, then min equals mid. small enough. Wait, is that what we're looking for? If it's small enough? Yeah, if it's small enough, then move the min up. All right, cool. So then we want to return, well, int right, or last legal equals min. Return last legal minus first legal plus 1. Okay. So now we have this method that works. Yeah. All right, so now we need our DP. So int array DP, new int n. So this stores how many numbers work starting at the first I. Let's call it x, so it matches what I have written on my sheet of paper. So for int x equals n minus 1, x is greater than 0, x minus minus. So why are we doing it like this? Yeah, because we look at future stuff. Plus 1, I guess. So if occurrences, or n occurrences at x, if this is equal to 0, then we can just leave the DP being 0, because 0 things will work. Otherwise,
Always a pleasure hearing you work, sir.
0, we have company.
Understood, sir.
Otherwise, how much time am I burning in this? Not too much, reasonable amount. Okay. So in other cases, we know that well, okay, so we can keep n occurrences of x. So we definitely will have this many work because we'll keep all of this number. So then if last index of x, well, okay, if n occurrences x plus 1, if this is equal to 0, then that's all we get. That's it, folks. Otherwise, if if last index of x is before the first index of x plus 1, that means that dp of x plus equals dp of x plus 1. That means we can continue from the first of the next thing with no recourse, I guess. No issues. Otherwise, then we're just going to have to deal with getting part of the last thing. Okay, so otherwise, dp of x plus equals n in range of the occurrences of x plus 1 from last index of x to n. Yeah, how many are in that range? And that will calculate our DP for us. So now we need to calculate our actual answer. So for index to 0, x is less than n, plus. So we can keep some prefix as well. So prefix is equal to if, okay, so int prefix equals n equals 0, 0, otherwise we do n in range for occurrences of x minus 1 from index 0 to the first index of x. So then ants equals map.max, ants, and then prefix. And that's what we're looking for. Okay, so there's a very, very large chance this doesn't work because that's kind of a lot of fairly complicated code. But it's worth trying. Array index out of bounds exception. Fantastic. If n equals 0, 0, otherwise, what's wrong with this? What have I done? Why is this an issue? -1, x equals 0, of course. 3, 4, 3, no. All right, test case number 1. Well, is there a simpler test case we can look at? This one they say is 1, we say 0. Okay, let's look at this. This takes 0 swaps. Well, yeah, this should be fine. So I guess let's just print this compressed thing. Zero, 1, fantastic. All right, so we're not majorly destroying ourselves yet. So then this n in range is what's wrong. So let's see. Querying. Querying n in range 0 to 1 for array 0. Oh wait, what is this? Ah, plus dp of x. Two, 2, 0, 0, blah, 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 16. Looks good to me. How many test cases? Large number of test cases. Okay. So F. Ooh, here's a strategy question. Which one do we submit? I think F2. No, we should have submitted F1. Because if this gets wrong, then it's like, well, what do we do?
Problem F2 got wrong answer test 3, sir.
Yeah, that's the that's the annoying part. Should have submitted F1. Oh man. Okay, that's very annoying. That's terrifically annoying. Darn. Well, I guess let's look through it for a minute. Man, I should have submitted to F1. Triple check compress. So we have our true set of values. We add everything in our array to the tree set, and we have this map to index +1, and then we set this thing to this index in the map. Okay, that's fine. we could stress test this. This list is certainly sorted, right? Occurrences. Did I add this thing? Yeah, okay. I'm going to just look through it for a minute. So if the list is empty, the answer is 0. If the smallest thing in the list is bigger than the rightmost, the answer is 0. If the biggest thing in the list is less than the smallest, the answer is 0. Find the first index bigger than or equal to L. The list at the mid is bigger than or equal to L, then move the right pointer over. Otherwise, this means it's too small, move the left pointer past it. Yeah, okay. First legal is equal to the min. So now, find the last index less than or equal to R. Reset these. If the middle thing, the thing I'm looking at, is small enough, then move the min over. Otherwise, if it's too big, then move the max over. Last legal loop is min, so last legal minus first legal plus 1. So this seems reasonable. So we get the first and last occurrence and the number of occurrences of each thing. Occurrences at this, add this index. First index of AI is max min, first index. Last index is max. Okay. I think that's fine. For each I, well, hang on, let's just pause for a moment here. Is the idea even right? Everything that you're going to move will be a prefix or a suffix of the sorted array. That's true. That's definitely true. So if you look at the things that wind up getting moved, that's going to be a prefix and a suffix of the sorted array, which means the stuff that you keep is a continuous range of values, but possibly with like only including some of the values of the biggest and smallest index. Yeah, so I don't know, I buy the solution idea. So now we calculate this dp. So if the number of occurrences of x is 0, then dp is going to be 0. Otherwise, we include all of this thing's occurrences. Yeah. Now, if the number of occurrences of the next thing is 0, then that means we're the biggest thing. So we can continue. Otherwise, we're not the biggest thing. So if our last index comes before his first index, then we can just build off him. Otherwise, we can't build off him. So we can only include a certain number of him in this range. Let's stress test all the 2's, I guess. 10, 5, that's 1. 5. Big number is 0. Alright, so 1, 3. So I'm resetting between test cases, surely. Okay. This seems right is my concern. Well, I mean, this whole thing seems right, so this should be, that's 0. So now 1, 1, 3 should also be 0. 1, 3, 1. This should be 1. I guess there are multiple reasons that can be 1 though. So what if we do like 1, 5, 1, 1, or 1, 1, 3, 1, 1. So this should be 1. But I've got the weird case for this. All right, so okay, so then let's or integer. Next int 10. Okay, so this should okay. My answer is -1. That is quite fun. What does this look like? 1, 3, well, let's make it smaller. How about that? Is equal to 2. Can we do something quite small? Past all right. About 3. All right, so L is 5, R is 1. Oh, yeah, I guess that's a... Does that matter? Does that matter? So if R is less than, or if R is less than L, return 0. So now this should be fine. Okay. Could that have happened? Come on, you can compile. Thank you. Number of range. Occurrences +1. This is the only time. Oh, here we go. Man, this is very confusing. Submit to F1. Wrong answer is quite... It's very much predicted.
Well done, sir. AC on problem.
What? What? Okay, I guess let's try F2 maybe then. I should have submitted to F1 earlier, man.
Problem F2 got wrong answer. Test 3, sir.
Okay. Well... That's super sketchy. Why would that be? What are the bounds for F1? No two elements are equal, and the array is tiny. Let me think for a bit. Alright, so there's no way the length matters. Like, that just doesn't make sense. So definitely the issue is that I'm handling duplicates wrong for some reason. Well, I guess now's a good time for a strategy question. So if this were rated for me, what should I be doing? Should I be doing D or F2? Should I be doing the problem that has 1,000 solves or the problem that has 41 solves? Good question, David. I'm gonna go for the one that has 41 solves because it sounds fun. I feel like an idiot, man. Why am I doing this problem? Alright, anyway. Am I missing any part of the problem statement that might make it harder? All right, so we know this is fine. Like this method counts how many are in the range correctly. Could my DP be wrong? I don't see why this isn't right. So let's go on to the problem that has over 1,000 solves. Wrote a string containing only lowercase letters. This string is known for you and given in the input. Then he erased some letters and wrote the remaining letters in any order that you would like. Now you have some string T. Now you're given. Oh, this is the distance from the first number. I see. I see. Oh, which is the one that has 0? There you go. What has 0? Everything that has 0 is the biggest. Everything else you just subtract from them. Silly mistake. Easy problem. All right. Do we have to extract it? We do. Oh well. Next, to carry array. All right. So this is int n equals this dot. Okay, so then it's guaranteed there's a 0, which means we need to find all zeros. Okay, so how do we do that? Well, let's like calm down for a minute and figure out how to do this. So we find all zeros in the array. And then we set them all to the biggest thing, and then we keep removing the biggest thing from the list of characters. So we can sort this. Can we sort this? Yes, it's small. Nice. So then all true, I guess. And then Boolean array killed. right, so then for int I equals 0, as this then zero. Okay, so then for int I equals 0, if int I equals 0, then zeros dot add I. Yeah, okay, that's fine. All right, so now for, well, int n killed equals 0, n killed plus equals zeros dot size, n killed is less than n, and by zeros, killed at I equals true. And then we're probably gonna have to do something else here, like set ants. Did I? Okay. So now their current equals, or I guess int line index equals line dot length plus 1. So well, their current equals line at line index. So well, line index greater than or equal to 0, and line at line index max minus line index equals current count plus line index max minus. So if current count is greater than or equal to zeros, then, well, if it's yes, do another one of these. So if it's greater than or equal to zeros dot size, then fill with current and break. Okay. Now we also want to for I equals 0, I is less than n plus if not killed at I, then a at I minus equals math.abs z minus I. Okay. What are the chances this works? AAC. Why AAC? Oh, I guess that's conveniently correct. Then this one. Wait, what? What's going on? ABC, there's one character. I print C, they print B. That should be fine. Okay. A, B, B. I print ABA. That matches them. This nonsense thing. And it's Codeforces. That's fantastic. Oh, hang on. What do we need to do for this? Very few queries, so no print writer. Fantastic. You know, it would take me less time to just add print writer than it would go check, but it's fine. Okay.
Well done, sir. I see you on problem B.
So let's solve set now. Daniel's doing not too bad. Thomas is doing pretty alright as well. Good to see. Then a bunch of other people are kind of tanking. That's a big delta though. Alright, well, let's solve it. Now the question is, why on earth am I wrong? Let's just yeah, okay. Thank you. Give me a break for a minute. Okay, so this is just very likely right. Like, this is this is fine. All right, so what would a brute forcer look like? I can brute force everything except the dumb observation, right? The dumb observation is some continuous range of numbers. Man, the idea's got to be wrong because this code looks so good. How much time do I have? I've got 30 minutes. I can do this in 30 minutes. What does generation look like? Generation is super easy. Let's just write a generator. So extent small stuff. Okay, so this should be cool. That is not right though. Yeah, that's fine. Okay. So now we have this file. Looks good. So now let's write the brute. So So we have the test cases. So int n equals a test dot read array n. Well, hang on, let me just really dumb. 1 5 5 4 3 2 1 before. Okay. Yeah. Well, why am I testing? So this should be 3. It's a dumb thing to test. Okay. Yeah, so now what do we need to do? We need to say so we need the smallest moved, biggest, or alright, so we need the smallest left kept, biggest kept, smallest thing that didn't move, the biggest thing that didn't move, and what else? I guess that's it. So now it's illegal if there is something bigger than smallest, less than biggest, and it wasn't kept. Also illegal if kept isn't sorted. So yeah, okay, so the smallest thing kept will initially be here.next. Biggest will be min. Equals 0. SS, what is this thing kept? Size kept get I is greater than kept get I plus 1. Then continue better. Okay, so now if we have to do another loop through here. Yeah, okay. So if kept mask, keep mask, and 1 left shift I is not equal to 0, then it's kept. Alright, so now we have the smallest and the biggest one that we don't move, and now we need to look through all of the things we do move, or all of the things. So we can reuse this logic. So this means if it was kept, otherwise, this means it was left. So that means if AI is less than smallest kept, or AI is greater than biggest kept, then we have an issue. Okay. And now, finally, this is okay. Then best equals math.max best and integer.bitCount keep mask. Cool. So let's try this on samples. 2, 5. All right, not even close. Why would it get that one wrong? How much time do I have? 20 minutes. This might be closer than I would like it to be. So I'm not counting we have no candidate masks? That's insane. I don't believe it. And it's 5. This thing is less than the smallest. Oh, it's yeah, it's greater than the smallest and less than the biggest. Then it's a problem. 2. Blah, 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 16. Okay. All right. File. Yes, come on. So now print, close. Okay. Give me my real F. Print writer out. It's new print writer. New file. fme dot out. And this needs to be come on. All right, now we diff them. Really? so we are wrong. That's good. Be right back. All right, so what is the first case that we're wrong on? 298? That's kind of insane. Really? Really? It's like 1 in 1,000. It's very unlikely. All right, 298. So Gen. All right, so that's annoyingly big. So the real answer is 3. What do we say? Nope. Unhelpful, please. We say the answer is 4. It's unfortunate. Why do we say that? Whew. Can we decrease this by 1? What happens if we do that? Then we get the answer right. No, wait, do we? Yeah, we still get it wrong. So they're telling me you can move 2 things here? What? How do you do that? Oh, like this, you take that. Damn, yeah, that's the case that I skipped. Yep, that would do it. It's a good case. It's a very good case. Okay, so now we just have to handle this. So x plus 1 or x minus 1. Yeah, okay. So if ai is not equal to 0, then ants equals math.max ants n in range from what is this going to be? Occurrences of a at I from 0 to a at I, or if a at I is not equal to n minus 1, plus in range from occurrences of a at I plus 1 to this is from 0 to position I, from position I plus 1 to position n. This should get me to, that's f brute. Minus 2. Wait, what? No, n minus 1 is fine. What? Why is this an issue? A at I 1, 2, 3, 4, 5, 6, 7. Oh, occurrences at a at I plus 1. 2. Good. Okay, so let us get rid of this. And let's try this. Oh, we don't need that. We need this. Comment these out. So now we read in this stuff, blah, blah, blah. Okay. So regenerate, rerun our brute forcer. Any day now. Come on. Whenever it's convenient. Oh, I didn't change it. I'm an idiot. Okay. Just sitting here waiting for myself to type in a number. Okay. Now, this one. Okay, now we diff them. Right. Fantastic. And now we just run samples and get our AC. Yeah, okay.
Well done, sir. AC on problem at 2.
All right. Well, let's take a look at the standings first. Yeah, solved in 19 minutes. So not a hard set by any means. Geothermal, nice job, man. Nice job, bro. Congratulations, sir. Well, so it was a very, very doable set for sure. D, I just didn't see because I'm stupid. And then F2, I had a bug on, which kind of ran into F1, but you know, still very doable. So let's go over the problems, I guess. Since this is the end of contest. So, all right. Short substrings. So what is this problem? Alice. Oh yeah, you have to guess the number. Okay. So what does this look like? Let's make a new whiteboard. So you've got like some string. Maybe it's like x1, x2, x3, x4, and then you're going to write down all pairs of them, all pairs of these numbers in order, and each pair has length 2. So you've got like x1, x2, and then x2, x3, x3, x4, and then you wouldn't have x4 to like this next thing, so this doesn't exist. So you can get every number except for the last one by just looking at all of these indices, like every other index, and the last number is just going to be the last number in the string. So that's how you extract it. It's very straightforward. Next one, problem B. So you're given some array, and oh, you want to swap some things. Yeah. So all that matters is the parity of each element. The actual value of the element doesn't matter. So if you have like here are your even indices, and then here are your odd indices. Maybe we'll make it 7 long. So if you have an odd number in an odd index, then that doesn't affect your final answer at all. And now if you have an even number in an even index, that also doesn't affect your final answer. So the things that matter is if you have an even number in an odd index, or if you have an odd number in an even index, like in these cases. So that's a problem, that's a problem, this is a problem, this is a problem. And it should be pretty clear that each time you do this, all of the changes you're going to make are you're going to be swapping 2 numbers that are both in the wrong place, and you're going to make them both be in the right place. Which means you need the same number of evens in odd indices and odds in even indices. So if you don't have that constraint, then you won't be able to pair people up, or pair indices up in order to fix all of them. So in this case, it'll be impossible, because we have 3 of these. We have 3 reds that need to be in a red place, and only 1 blue that needs to be in a blue place. So it won't work. But if these were both blue, for instance, then we have the same number of each group that needs to swap. So we just need to count the size of one of those groups, and that's the number of swaps we're going to make. So that's problem B. Let's look at problem C, social distance. So you and your friends are visiting a restaurant. Oh yeah. So this is I don't know, interesting, I guess. It's cool enough. So you have some 0s and some 1s. Then what you're going to do is you want to change some of these 0s to 1s. And you want to do that in such a way that like you maintain some social distancing requirement.
Always a pleasure hearing you work, sir.
Oops. 0, we have company still. Zero, we have company. All right, well, oh well.
Understood, sir.
There you go. So what we want to do here is like we want to maintain the distance between any pair of 1s. It needs to be at least 2. So what we can do is we can do this in linear time, because we know there are certain positions that are going to be impossible to put anything in, regardless of, even if we put nothing down, there are certain positions that are totally useless. So if it's 1 to the left, I guess if it's up to k to the left of any 1, then you won't be able to put something there. So in all of these positions that I've crossed out, we can't put something there because there's something on the right that would make it impossible. And then similarly, if it's 1 to the left of a 1, then, or if it's up to k to the left of a 1, we can't put anything there either. So we can ignore all of these elements, and we can do this just with a sweep from left to right and from right to left. And then we'll have a counter of like what the distance to the nearest 1 is on that side, and if it's too small, then we'll set it to 0. So when we're done with that, we have a bunch of candidate positions. Let me modify this array in just a slight way for it to include the other interesting case. So if it's, let's say we add another 0 here. All right. So now what we can do is we can greedily place 0s in the first position possible, or greedily place 1s in the first position possible. So this is free. So since this is free, we can like turn this into a 1, and that's fine. Now we get to this next 0, we turn this into a 1, and now we have to remember that we have to mark some x's on the right side of this 1 that we've already marked. Yeah, and I guess that's it. I'm sure there are a bunch of other ways you can do this. If you use like a tree set and you look at the first thing higher and lower than you, then each of these zeros, it's very easy to see whether or not it's valid. But you can just do it in linear time as well. I don't think time would have been an issue for this problem because you had 2 seconds and bounds were pretty small. It's a very easy problem. Problem D, task on a board. What was this one? Oh yeah, I struggled with this one. Holy cow, dude. So it's very obvious in hindsight, but I just didn't see it for a minute. So you have, the problem's like a bit tricky to explain, but like you're given some string. Maybe like initially you have just some group of letters. So maybe you have A, B, and C, and their order doesn't matter. Then what's going to happen is someone's going to make a string out of these letters. So maybe they make the string BAC, or I guess AAC is the string that they make. Then what they're going to do is for each letter, they're going to find all other letters. So like maybe all other letters that are bigger than it. So like you find this C for this A, and then you add the absolute value of your distance to this C. So this would be 2, this would be 1. And now this C has no numbers bigger than it, so its total is 0. So then when you're done with that, you've got this array here. It's like 2, 1, 0. And now what the problem is if you're given this set of numbers, or this group of letters, and also this array, your task is to come up with one of these red arrays that would solve the problem in the intended way. That would give you, like this red array has to have only numbers from this group, and it also has to give you this array if you calculate this array as you would in the problem. So they also guarantee that it's possible to. They should say like a constraint is that it's possible, but I guess this is fine. So since they guarantee it's possible, what does that mean? Well, what numbers have 0? The only numbers that are going to be 0 are numbers that have nothing bigger than them. So what we can do is we can, if we have some array, like maybe array is like, I don't know, some things that aren't 0, then maybe a 0 here, and then some more stuff, then another 0. This thing is going to be the biggest of all of the letters in the entire group. And this thing will also be that biggest number. So we can look through our group of letters, and we can like look from biggest to smallest and find the first letter that has 2 or more examples of it. And we know the only place that letter occurs are in these 2 positions. There are no other versions of that letter. So we can delete all letters bigger than that, and we can delete all of those letters and just put those letters here. So maybe like if that's like an F, maybe we have 3 Fs or something, and we put an F here, we put an F here, and then we delete all of these Fs, and also anything bigger if they're like Gs or Zs or whatever. Okay, so after we do that, what we can do is we now know that these are Fs, which means we can update all of these other positions because we know they're all smaller than this F. So here we can subtract 1 from this. We can subtract 2 from this. We can subtract 1 from this. Subtract 2 from this. This one's already used, so ignore it. This one we subtract 4 from, all from this F. And now from this F here, we can subtract 1, subtract 1, subtract 2, subtract 4, and subtract 5. After we do this, there's going to be some new biggest number, and it won't be F, it'll be something smaller in the alphabet. So maybe it's like a C or something. And maybe this number is a 0. Well, we know since this is a 0, we know this is going to be the next biggest number. And we can repeat this because now we've pretty much just removed these Fs from the array. We've also removed all contribution of them from the array. So now what we can do is we can like repeat the method and see, all right, find any zeros, replace those zeros with the biggest candidate letter that will actually work, and then adjust all of the other like totals on the array accordingly. And if we do that, we'll very easily get the resulting array. So I guess the big observation, which I just didn't make for quite a while, is that you don't need to, but it's very helpful to look at things from biggest to smallest, and the biggest thing is always going to be the thing with the 0. All right, contest is over. But we have 2 more problems to review. So let's look at them. Problem E. So problem E was quite easy. I thought easier than D. So in problem E, you're given a bunch of letters. Their order doesn't matter. So maybe you're given A, B, B, C, C. We'll sort them because that's easier. And all that matters is like how many of each letter you have. And now the thing is, or the thing you're trying to do is you want to make some necklace, like some circular string that has a period of a divisor of k. Let me move this so I'm not blocking it. So you want the period of the string you make to be a divisor of k. So let's say k equals 12. Then you want your period to be equal to 1, 2, 3, 4, 6, or 12. And then whatever your period is, you want to use the letters in this string as many times as possible to like make as many copies of that period as possible. And then once you've made all those copies, then the total string length is going to be the period length times the number of times you can make the period. So what we can do is we can brute force this period, and the total number of candidate periods will be k to the 1/3 power, because this is roughly how many factors a number can have. So you have k to the 3rd, and that's how many periods you'll try. And then for each of these, you can just, you can binary search, but you don't even have to. You can just like naively brute force the number of times you can make it. And clearly you can't make it more than n. So this is like at most n. Because you can't make a string longer than just n total.
Pleasure hearing you work, sir.
Man, what? Okay. So then after that, what you can do is if you know what the period is and you know how many times you're going to make it, then you can say, well, if we're going to have a period that's some length and we're going to make it twice, that means if a is going to be used in this period, we have to use a twice. So why is that? Well, like, we're going to have this group of letters, and then we're going to have this other group of letters after, and these two groups have to be the same. So if we're going to put an a in those groups, and we want to use like as many of these a's as possible, then we're only allowed to use one of each a. And then similarly for b's, like let's say we have 5 different b's. Well, we need to split the b's across 2 groups, and we need the same number of b's in each group, and then we might need to throw away some extra b's at the end. So if we put 2 b's in each group, then
I don't understand what type of music.
0, we have company.
Understood, sir.
Alright, so then we can put an a and 2 b's in each period, and then if we're able to fill up the total length of each period, then I guess we're good to go. So then we can make this period, and we've brute forced the number of times we're going to make it. So then I guess this is times 26 is the final runtime. It's relatively quick. Okay, time for the last problem, problem F. And I'm just going to talk about the hard one because the easy version is pretty straightforward, I think. Or I don't know. I don't think it's as interesting. So that's why I'm just going to talk about the solution to the hard version. So in problem F, you I forget the problem. I'm going to have to go read it for a minute. Problem F. What's this problem? Oh yeah, you have to sort an array given the, like you've got 2 operations. So maybe your array is like 2, 7, 0, 4. And one operation is like take some number and move it to the beginning, and one operation is take some number and move it to the end. You can do either of those operations as many times as you want, and you want to sort the array. That's the problem. So I guess the main observation is if you have like some numbers, maybe you've got like 0, 0, 1, 2, 2, 2, 3, 3, 4, 4, 4, and 5, and then I guess maybe a 6. The first thing to notice is if you don't have these numbers like in sequentially from 0 to whatever, maybe this is a 10, then you can coordinate compress these numbers so that you use every number from 0 to the biggest number, and you use each of those numbers like some small number of times. So if this was like a 7, you can delete the 7 and turn it into a 5. And now the problem's the same. So you can like compress all of your numbers so that they're in some small range. That just makes it easier to code. After you do that, the thing to notice is that if let's look at like maybe the numbers that you don't move. So maybe these numbers, you never use some operation on them. That's fine, because you keep these numbers here, and then what you can do is first you can move this to the end, to the right end, then you can move this to the right end, then this to the right end, then this to the right end, then this to the far left, this, this, and this. And if you do that in that order, then you'll be able to sort the array. So, okay. What does that tell us? Well, basically, the numbers that we need to keep the same will be some continuous range in the sorted list of numbers. So we want to find the biggest continuous range that we can pick that makes this work. The numbers that we pick also, like, since they don't move, they have to be sorted in the original array. So what our goal is to find the biggest continuous range of numbers, or not continuous, the biggest continuous range of values, I guess. So the values are continuous, where they are sorted in increasing order. And what we can pick some of the 2s and maybe some of the 4s, but what we can't do, like this isn't a legal set. We're not allowed to pick some of the 2s, some of the 3s, skip some 3s, and then pick some 4s again. So what we can do is we can, to actually solve this problem, we can keep track of all of the indices of like each number. And if we know all of the indices of some number and we have those in some sorted list, then we can say in some, like this is our array, and we know that 2s occur at positions 1, 2, 3, 4, maybe 5, 6, and 7. Then we can use binary search to find how many 1s, like these are all, there's a 1 here, there's a 1 here, a 1 here, 1 here, 1 here. So we can find how many 1s are in like this range. So maybe like we're querying this range here, and we want to see how many 1s are there here. And we can do this in log n time with binary search. So once we have that, the rest of the problem is just an easy DP. That's kind of like the main tricky part of the problem. And also there's another tricky case that I missed for a bit. So the first thing you might want to handle is we're going to do a DP. Well, okay, so the first thing to handle is you can keep a couple things. The first thing you can do is you can keep you can keep all of the indices of some number. So like keep all x's. And that's obviously possible because all x's will be continuous. So this is illegal. The second thing you can do is you can keep a bunch of like x's, and then you can keep some x plus 1s. And this is the one I forgot about, but this is like a very important case as well. So what's a case where you need to do that? You can have like a 2, then a bunch of 1s, and then a bunch of 2s, and then a 1. So you can keep all of these numbers. And that's a legal thing you can do. The last thing you can do, and this is kind of interesting, I guess, is you can like keep a bunch of x's, but maybe you ignore some x's as well. Then you can keep some x plus 1s, and this will be like all x plus 1s. And then all the way up to some y. So you keep like all numbers that are between x and y inclusive. and then maybe some y plus 1s. Not necessarily all of them, but just a couple. So these are the three types of groups that you can use. So the important part here is if you take any x's, then you have to take, and you take like some number bigger than, oh sorry, these shouldn't be x plus 1s, this is y plus 1. So if you take all of the x's, or if you take, sorry, if you take any x's, and you take any number bigger than like x plus 2, you have to take every x plus 1. So in order to handle that, what we can do is we can do a dp, where like dp of I equals like how many numbers you can keep. Like the number of keepable things if we take the first I. So now there are two cases to this. Since we know the next number is going to be I plus 1, so if the last thing of what we want to keep, if the last I comes before the first I plus 1, that means we can take all of the i's, and then we can continue maybe taking all of the I plus 1s and then doing stuff after that. So in this case, the answer is like the number of i's plus the number of, or plus dp of I plus 1. The other case is if we're taking some of the i's, but then after taking all of the i's, we can't take the next I plus 1. That means the last number we take has to be either I or I plus 1. So then this is like the number of, is like count I plus, well, okay, so it's the number of i's, because we got to take all of those, plus count I plus 1s in the range of the last I to the end of the array. So this will be the number of elements we can keep if the first thing we take is the first I, and we can't take the first I plus 1 after taking the last I. Might be helpful if I draw like kind of an example of that. So if we have like some 2's here, and then we have a 1, or a 3, and then we have some more 2's, and then maybe like some more 3's. So if we start, and we can have other stuff over here as long as they aren't 2's. So if we take the first 2 here, then our ranges of 2's have to be, we have to take all of these 2's. And now since the range that we keep has to be sorted, we aren't allowed to keep this 3. Because we took this 2, we're going to have to take all of the 2's. And we can't take this 3 because it won't be sorted. It'll be before some 2 that we want to take. So then after that, we're allowed to keep some 3's, but we can't keep anything bigger than 3. So we'll just query this range and be like, how many 3's are here? And maybe there are some 4's as well. So we just want to query how many 3's are in this range. But for dp at 3, that will take this first, dp at 3 will take this first 3. Take this first 3, and we want a 4 over here too. So it'll take this whole range of 3's, and now if there are 4's, or maybe there are things bigger than 4 over here as well, then maybe like this. So now this will look at dp of 4, which will take all of the 4's and maybe some 5's as well. So that's kind of how the dp works. And then finally, this is missing one part that's kind of helpful, I guess, which is if we're looking at, man, I have all of this stuff here that I don't want. Kind of just clutters up the screen. So let's say we're looking at this dp of 2. So dp of 2 will take all of these 2's, and then it'll also add these 2 3's in addition. We can also take the things right before the 2's. Since we're taking all the 2's, we can take some of the 1's as well. So we can also range query for the things before the first 2, how many 1's are there. And that will give us what we want. So yeah, I thought this was a pretty cool problem. This was definitely rather interesting. Some of the Div3 problems just get a little uncomfortably easy, but I thought this was a good problem. Interesting. So hope you enjoyed the contest. Hope your rating went up, and I'll see you on the global round on Thursday. So that should be fun. Finally, a round rated for Div 1.